So this week, this is the class I believe for the first class of the new year, right? So I couldn't start a new chapter because the previous chapter is not finished. So we start from the portion where we stopped. Okay. So I hope you have understood. Four or I believe 5 points were made regarding the surface tension parts, right? And extra pressure or excess pressure in the case of drop inside the water, that should be mugged up. Okay, those are all of them both important in the case of your NEET preparation as well as your school preparation. Don't differentiate it. Okay, so let's move on. Today the topics, small topics which I'm going to take, starting is from where is actually based on our NEET, not your CBSE, but it's better if you don't segregate it as a NEET, etc. Okay, so this is not a sentence, guys. It is actually the continuation of what you say as first we dealt with the extra pressure, remember, in the case of drop, right? As well as we saw a drop inside a liquid, right? Spherical bubble, etc. Right, spherical drop, and we found the excess pressure as 2s by r, right? And then we dealt with the spherical bubble and we found the extra pressure as 4s by r, and in the case of air bubble inside the liquid, it is 2s by r, right? This is where we stopped in the previous class. From here I am continuing today's video. Okay, suppose there is a small drop of water. It is squeezed between two parallel plates like this, right? Now the pressure inside this water is less than the atmospheric pressure, right? Which is acting on the plates. There are two atmospheric pressure here. So the excess pressure or the pressure inside this drop is less when compared to the atmospheric pressure here, right? And the difference in the pressure between atmospheric and this inside pressure or the excess pressure is given by P is equal to 2s by D, where D is the separation between the plates, right? As you can see, that means this D is actually you can say this radius, if I can say, is half of D by 2, right? So even if you want, you can write this equation in terms of radius also. How it becomes will be 2s 2r, or you can just write it as s by r, no pot. So it is better to learn in terms of separation between the plates, right? So if there is a liquid drop in between two parallel plates, the excess pressure between, or the difference in pressure between the inside pressure and the atmospheric pressure is 2s by D, right? Now the same question can be asked with respect to area, right? If area A, right, there is an area over which the liquid wets the plate, right? This plate is wet by an area A, then the force is required to separate these two plates. You would have seen this one, yeah. You take two glass plates, you have water drop inside. It means it is difficult, little bit difficult to separate this plate from here. So how much will be the force I have to apply there? There, force is equal to pressure into area, right? So this is 2s by D into A, right? So I hope you found three equations, that is the pressure difference between the liquid here and atmospheric pressure is 2s by D, and D in terms of R is equal to D by 2, as you can see in the figure, and force which is required to separate these two plates which is having a liquid between them is F is equal to 2s by D into A. Clear? Right? So this is the next topic or point I want to discuss after dealing with the excess pressure of a bubble inside liquid, right? Now suppose two bubbles are coileous. Coileous means, coileous spelling is Coaleasce. Coil mean by coileous is when suppose there is a small bubble and another bubble, they mix to form another large bubble. That is the meaning of coiling, mixing of two bubbles. That's the meaning of it. Okay, I hope that much is clear. Suppose when two bubbles are isothermal condition, that is the temperature is constant and they are coalescing to form a new bubble. Then constant temperature means that you would have learned in your lower class. Then PV is constant, or you might learn later on, right? PV is constant. Now let R1, suppose this be a small bubble, or a small bubble which is having radius R1, and another bubble which is having a radius R2, right? Right, and the new bubble which is formed by the coalescing of them is having radius smaller, right? Let's say this bubble having pressure P1, this one is having pressure P2, and this is having pressure P. Then I can write P1 V1 plus P2 V2 is equal to PV. As per PV is constant, sum of PV, total P pressure into volume product is constant in isothermal condition. I can write this formula, right? Now, what can I write about each pressure, right? Pressure in terms of surface tension, right? So P1, right, and V1 is easy, 4 by 3 pi R1 cube, right? What is pressure? This is the case of bubble, right? So two soap bubbles, right? So one soap bubble's excess pressure, you have learned it as 4s by R, or 4T by R. In some of the books it is written as T, but I hope you understand. Spherical bubble, two free surfaces, so it's in air, right? So I will write it is 4s by R, right? Similarly, this will be also 4s by R2. This is R1, this is R2, right? Into 4 by 3 pi R2 cube is equal to 4s by R, 4 by 3 pi R cube, right? Now all the terms are having 4 by 3, 4, 4, and 4s, 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 right? Pi, 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 etc. can be cancelled out, right? Clear? So I can remove this RQ and this R can be cancelled, so there will be R square, right? So from here I can write R squared is equal to R1 square plus R2 square, right? Or I can write R is equal to R1 square plus R2 square. You got a general equation. That is, if two bubbles of radius R1 and R2 coalesce to make a bigger one with the radius R, then this bubble will have a radius of R is equal to root of R1 square plus R2 square, right? This equation is better to learn by heart. You can see that type of questions in your material also, right? Right. Now, radius of interface, this is another case. This is another case studies. Okay, when two bubbles of different radii are in contact, suppose this is a drop, let's say it is having radius R1 and is in contact with another, let's say this is R1 radius, this is R2 radius, and this is the interface between them, right? Two soap bubbles, right? And they are in contact as shown in the figure. Now let the radius of the common boundary, right? Let's say that common boundary is having a radius of R. Now let P1 and P2 be the express pressure of the two sides of the surface, right? This is having P1 pressure and this is having P2 pressure. Then the resultant pressure will be P is equal to P1 minus P2 for this intersurface. Yes. So I can write for P, that is 4s by R. P1 will be 4s by R1. P2 is 4s by R2, right? Now we know R1 is very small when compared to R2, right? So, and this equation can be written as 1 by R is equal to 1 by R1 minus 1 by R2, right? Or I can write R is equal to R1 R2 divided by R2 minus R1, right? Clear? That is the radius of the interface, right? This one's radius, this one's radius. When two bubbles of different radii are in contact, is R is equal to R1 R2 divided by R2 minus R1. This much clear, right? Now another thing you have to know is work done in forming a liquid drop of radius r, or surface energy of a liquid drop in area air. Right? This and all are topics. You have to write it as heading in your notebook. You are asked to find work done in forming a liquid drop of radius r, or work done can also be talked in terms of energy, that is surface energy of a liquid drop in air. So how can I find it? See, it is a liquid drop, right? So work done or energy, surface energy, is equal to what? Surface tension into area, right? We have talked about it. Remember, surface tension is equal to surface energy by area, or surface energy is equal to surface tension into area, right? Why didn't I write into here? Surface tension into area, right? So similarly, it's a liquid drop, right? Liquid drop means it is having a surface tension, that is I'm taking as S. Area is what? 4 pi r squared. Drop, we usually take it as a spherical form, right? Similarly, if we are asked an extra topic, I am asking, if you are asked what is the work done in blowing a bubble of radius r, bubble, okay, you are asked how much is the work done to blowing up, that is how much work I have to draw or give so that this bubble enlarges itself, right? So it is very easy. Work done, again remember, it is surface tension into area. Now bubble means there are two surfaces, right? It is not in liquid, it is in air, so two free surfaces. So I will write it as 2 into, right, surface tension, and area will be 4 pi r squared. So it will be 8 pi r squared s. Clear? Right. Now similarly, let's move on. And this is the same equation if you are asked work done forming a soap bubble, right? You, in the case of soap bubble, it's also the same expression, right? Clear? Similarly, if you are asked the work done to increase the surface area of the soap bubble, this is the work done to form a bubble, right? The form a bubble was not there, you are making a bubble, right? If you are asked already there was a bubble, it had an area r1, you want to change its radius to r2, you want to enlarge it, means then the equation becomes 4 pi s, then into what? R2 squared minus R1 squared. General formula from this one itself. Clear? Initial radius is R1, mu radii is R2. We can generate that also, right? Now similarly, work done in spraying or breaking a liquid drop of, suppose there is a very large repeat drop of radius R, right? You want to convert it into small drops like this, right? So that there are, let's say there are n number of drops like this, right? Clear? And each drop, let's say, is having radius r, right? I'm going to convert this one as more like this, right? Each of them, or we have drawn it, each of them is having r as radius, and like that I want n number of drops, right? So how much work done I have to do? Clear? So you have to find, so if you want to find work done in spraying or breaking a liquid drop of radius r into small n identical liquid drops of radius r each, right? And it is given by the difference in the surface energy of the smaller drops and the larger drop, right? How much energy or how much work done I am going to do to convert this into this, means I just have to find the difference in the surface energy, that is work done is equal to surface energy of these small drops. There are n number of small drops into their area, right, into surface tension minus what is the work or energy of this guy, is 4 pi r squared s. What is the relationship between larger radius drop and the smaller radius drops? That is, see, this was a condition. It was converted to n number of small drops, and each were having radius r, and this bigger one is having radius capital R. Now we know the volume is not going to change, right? If this entire drop is having volume V, then the n drops total volume will be also has to be V, right? So I can say V is equal to n into small v, where each v, see, this was having volume V, this is small v like that, and n number of total volumes of small v will constitute the larger volume V, right? So I can write what is the volume of the larger drop. I can write it as 4 by 3 pi capital R cube, and the volume of single drop will be 4 by 3 pi small r cube. So I can cancel these two guys, or I can write r cube is equal to n into small r cube, or I can write capital R is equal to n raised to 1 by 3 into r, right? Or I can make this small r is equal to n raised to 1 by minus 1 by 3 into r. So better if you make this as a column block or whatsoever and keep it with yourself. Now this expression is required while we calculate the work done equation here, right? Now let me remove this much portion. Right, I hope you understood the derivation part, right? Now this section I can write n 4, this is pi now, pi, right? This is r squared. In place of r squared, I'm going to write n raised to minus 1 by 3 into capital R squared s minus 4 pi r squared s, right? Now this can be written as n into 4 pi n raised to minus 2 by 3, just 2 by 3 r squared s minus 4 pi r squared s, right? Now this n and this n raised to minus 2 by 3, right? So that means 1 minus 2 by 3, it's n raised to 1 by 3. Or I can write 4 pi r squared s, for r squared s is common, n raised to 1 by 3 minus 1. This is a general formula which is for the work done for a larger droplet to be splitted into smaller droplets of or n number of droplets. Clear? Right? Better you can mug up that equation. Now suppose the next point which we are going to deal is force which is required to lift a needle which is floating on a liquid surface. That is, this is the liquid surface. On that you are going to keep a needle, right? So how much is the force I require to lift this needle upwards, right? Clear? So when I in place here, I am going to draw this needle as a single unit. Let's take this as a needle, right? I require to do some force to be applied upwards so that it can be lifted up. This needle will be having a weight downwards, right? And there will be two surface tensions due to liquid, right? There are two sections here. So this is SL and this is SL. That is a surface tension. This S is surface tension and L is the length of the needle, right? So that becomes, see, I hope you remember there is a relationship between surface tension and force, right? Hope you remember it. That is, force per unit length is actually surface tension, right? And I hope you remember we treat it as a 2, or I hope you have derived the equation F by 2L is equal to S, right? So F is equal to S into 2L, right? I drew it as two separate so that you can understand how it came up, two free surfaces, right? That is equal to, I can write F is equal to mg plus 2SL, right? Clear? So this is a general equation you can write. Simple, right? Now similarly the next case, this and all are neat topics, but better you can learn and don't take it as a separate one, right? Excess force which is required, because that drops etc is usually there in your NCERT textbook as a numerical problem. Now excess force which is required to lift a circular ring, right? Suppose this is a circular ring, annular ring, that's what you call, right? This is an annular ring, right? It is having a, let's say, an internal radius r1 and an external radius r2, right? So it is floating on a liquid surface, right? So how much force we have to apply? So just like this, there will be a force upwards. So these two surfaces will be having its own downward force, right? Clear? That will be surface into what? Circumference, because it is a circular section. So S into this guy will be having its length, means it will be its circumference, that is 2 pi. This is radius r2, right? 2 pi r2. And this guy will be having S into L. In place of L, I will write circumference, that is 2 pi into r1. So the above force F is equal to S into 2 pi, or I can just write it as a general formula, na? 2 pi S into r1 plus r2. Right. See, I have not constituted the weight because the ring section's weight is negligibly small. Right. So usually if it is just a simple ring, that is you are only considering only single ring, then its R1 and R2 will be equal, right? So it will be, general formula can be made for a ring, only a ring, not an angular ring. That is, you are not considering two situation, you are having a ring, just a ring. Right. So 2 pi S r plus r will be 2, so it will be 4 pi rs or sr. Now if it is a disk, right, disk, then the inner section's radius you don't consider, becomes this entire thing becomes like this, right? So there is no vacant space here, right? So I can recollect this radius section, I will only consider the outer radius. So the force will become what? Force of a disk will become 2 pi sr or rs, right? This is not a general formula, better to study. Okay, now let's move on with your basically about your textbook portion. Okay, that is, why does this is a repeatedly asked question, why does water stick to glass but mercury doesn't stick to the glass? And after this we have to talk about capillarize, etc. So this first question, similarly there is an application of why you are learning as a first tension, etc, etc. So first question which is usually has been asked in your examination is, water will stick to what? Glass, but mercury doesn't. Why? See, in the case of water and glass, right, water sticks to the glass because the surface energy of water and glass, right, surface energy of water and glass, right, is less than the surface energy of water and air, right, right, between the glass and air. That is, see, if I consider the water air interface, right, and I consider surface energy of glass and air interface, right, if they sum up, right, even then the surface energy between the water and glass is very less, right? That is, if I consider this as the surface of glass and I have dropped a water droplet here, so the surface energy of water and glass is very less when compared to the water and air, right? This is water and air, and glass and air, right? So surface energy of water and air and surface energy of glass and air is very high compared to the surface energy between water and glass, right? Whereas in the case of mercury, the surface, and similarly I have dropped a glass and this is our mercury, it occupies what? These surface area. Now, surface energy between the mercury and glass, I will write it as surface energy between mercury and glass. Alright, it is very high when compared to the surface energy between mercury and air plus surface energy between glass and air. Right, that's why it doesn't stick out, because its surface energy is so high, right? So it cannot stick, it has a high condition to flow like this, whereas water surface energy is very less, so it maintains here itself. Clear? Right, so this is the reason for it. Now this is explicitly asked as it is. Now the next type of question which is asked is, how does a detergent work? How does detergent work? See, washing along with water can remove some of the dirt, but it does not remove the grease stains, right? This is what you see in advertisement, right? This is because water does not wet greasy dirt. Does not it's this is your cloth, it is having greasy section, oily section. This cannot be wetted by water. So that's why we require detergent which mixes with water, right? And then this dirt can be removed from the clothes. Now what is the shape of detergent? It is just like hairpin. That's how you I believe you have learned little bit about how detergents work in chemical form in your chemistry. If not, you will learn later on study. Here we are not going to learn about the chemistry, etc. Okay, we are going to deal with what surface tension parts. See, it has an hairpin shape, and when we add the detergents in water, right, one end of the stick, suppose this is water, right, one end will be sticking to the water surface, the other will be, suppose this is the water surface, the other surface will be sticking with the dirt, right? As a result, suppose this is a dirt, so this is a detergent which I have done, this is pin shape, right? So as a result, the dirt is getting attracted to the detergent molecules and they get detached. This is a soft cloth piece, right? So what had happened, this is the water, sorry, the soap molecules which are pin shaped. One end is attracted to water, the other end is attracted to the dirt. So now this dirt entire is locked by the detergent molecules, right? The detergent molecules now, since this part is attracted with water, when the water is dried off or when the water is removed, this also moves with water, right? The entire thing moves along with water, hence pulling the what the dirt along with it. Clear? Right? I hope you understood. It's very simple. Right? This is how our what detergent works about. Very easy, right? So I believe you can guys, there are good figures in your textbook. I would recommend you look into the textbook's figure. Now the next topic, which is very important in case of your NEET etc., is angle of NEET, or this is your textbook NCRT topic. Okay, angle of contact, usually it is theta. It is the angle at which a liquid interface meets the solid interface. Suppose you are having two capillaries, or I can say two tubes, right? You know what is lower meniscus and upper meniscus. This is lower meniscus, this is upper meniscus, right? This is for water, this is how water is seen. Whereas mercury, when you have it in tube, it will be like this, right? So free surface of the liquid, right, the free surface of the liquid in contact with the solid bends at the point of contact, right? This is bending at the point of contact, here there is a bending at the point of contact, similarly here and here, right? The angle of contact is the angle between the tangent to the liquid surface, the tangent to the liquid surface and the solid surface, right? This is theta here. This is the angle of tangent I have drawn, then the tangent and the solid surface. The angle between the tangent to the liquid surface and the solid surface is known as, and should be measured inside the liquid, okay, not outside the liquid. Similarly here also, right, this is a point of contact, so I have to draw the tangent like this. So what is the angle? It should be inside there, right? So this is the tangent and the solid surface, this becomes angle, right? It should be, I cannot draw this one, why? That is outside the liquid, right? So inside the liquid, so this becomes the angle of contact. Clear? Right? So I hope you understood. Now, what is the significance of the angle of contact? You can see, right, here the angle of contact, this is acute, this is obtuse. Obtuse means greater than 90, less than 90, right? Right. So the angle can be acute and obtuse or obtuse depending upon the nature of liquid, right? Now if theta, that is the angle of liquid or angle of contact, if it is greater than 90 degrees, like this one, right, then the liquid does not wet the solid surface, it will not wet the solid surface, and this meniscus is convexing up, right? So when theta is greater than pi by 2, liquid does not wet the solid surface, right, and the meniscus is convexed up. As you can see in the figure itself, this one, right? Now when theta is less than 90, right, So this will be opposite, it wets, just like water wets the solid surface, right? And it will be concaving up like this. In the case of water, this is concaving up, right? So the meniscus is concaving up, right? Simple. Now when it is equal to 90, that is theta is equal to 90 degree, then the liquid wets the solid surface, whereas the liquid, that is the figure, if I draw, it will be just like this. There is no upper surface or lower surface, or there is no meniscus at all. That is, it wets solid surface but no meniscus, right? That is, the liquid surface is flat. Liquid surface is flat, right? So just looking or knowing the value of angle of contact between a liquid and a solid surface, you can say how the liquid will look up, right? Clear? Now similarly, there are some of the things more I have to talk about, right? You can even say, based on this one itself, by looking at the angle of contact, you can say whether the liquid will be spreading, right, on the surface of a solid, or it will be forming droplets, right? Spreading means like this, droplets means this one, right? Okay, so if the angle of contact is obtuse, that is when theta is greater than 90 degree, then you can say droplets are formed, right? That's why we talked about mercury forms droplets, right? When the angle of contact is greater than 90 degree, spreading happens, right? That is what happens when, see, water is dropped on a solid surface, it spreads. Whereas mercury, if it is dropped on a surface, it forms droplets, right? So angle of contact, we can say in that term also. Clear? Right? Now we can, in as per your textbook, there are some of the figures you have can see, right? And after that, shape of meniscus, etc., I will talk about that also, and you will be taught what is the difference between droplets and bubbles. Okay, so listen to this one. Suppose this is a droplet, right? When we are going to talk about case 1, when the droplet is formed, right? We are talking when the droplet forms, when the angle of contact is obtuse, right? Consider we are having a solid surface and a droplet of water, which is the liquid, and we are having air here, right? Solid and liquid interface is, let us show it is SSL, right? A solid surface interface, right? SSL means it is, let's say this is the interface, SSL, that is solid and liquid interface, right? And solid and air interface, I'm going to show it as SSA, that is solid and air interface. All right, clear? And liquid and air interface, I'm going to show it as SLA. So how would I say? I have to draw a tangent. Why it doesn't look like a tangent? Right, I drew a tangent between the solid and the liquid. Right, inside the liquid I have to make an angle, so this becomes theta. So this is angle of contact, right? This is our SLA, liquid and air, right? Clear? Right, liquid and air, I have drawn a tangent, and the angle between the tangent and the solid surface, that is angle of contact, right? The angle which the, I can say, actually from the figure I can say the angle which SSL, that is the interface between solid and liquid, right, makes with SLA, that is liquid and air, I can say this is greater than 90 degree, right? So that is the droplet is formed. So I can explain by figure also, right? Similarly, when the spreading happens, case 2, this is what is drawn in your textbook. That's why I am taking it as an exclusive in the form of that figure itself. Case 2, when spreading, same, right? This is SSL. Yeah, suppose I have considered this is a solid liquid interface, and this becomes a surface between surf and air. right? Surface and air. So when the case of spreading happens like this, right? This is how spreading, the tangent will be like this, SLA. So you can see this is the angle of contact, this theta is less than 90 degree, right? So simple, right? Repeatedly asked question which is usually asked is why the water as well as in most of the liquids, depending upon the surface, they have a tendency to acquire this shape. This main shape means spherical shape. Why they have the tendency to do so? Now, that is basically the reason is that whenever liquid is left to itself, it tends to acquire the least possible surface area, right? So that it has least surface energy, right? Because how much the energy or area decreases, that much energy, surface energy decreases. So always any type of liquid always has a tendency to decrease its surface area to reduce the surface energy, so that it has more stability, right? For more stability they acquire the shape of a sphere, because sphere is having the least possible area. So I hope you understood. That is a small question usually asked. Now somewhere I have seen in your textbook also, I have seen the difference between drop, cavity and bubble, right? What is the difference between the three guys? See, drop, it's spherical structure, right? And this spherical structure is filled with water or liquid, right? There's only one interface on this drop, right? Clear? So the interface separates this water and air. This is air. Let's say this is water itself. So this is water and there is only one interface between them. This becomes drop. Example, water droplet. It's an example of drop, right? What is a cavity? Right, it is in this suppose there is water and the middle there is air, that is bubble. In suppose this is an aquarium and you are considering a bubble, so here it is air, right? Clear? And the surrounding there is water, right? Then this is cavity, inside air, outside water, inside water, outside air. I hope you found the difference between cavity and drop. Now what do you mean by bubble? Bubble, there is two interfaces. Suppose I draw actual a bubble, it is actually like this, right? There's two interfaces. One is air and another is water. See, air, water and water, air. If you didn't understand, this is air. This layer is actually water and outside again it is air, right? So here air water interface and here there is water air interface. This is what is a bubble. So it consists of a thin film of water. There is only a thin film of water and inside this thin film there is air and outside also air. So soap bubbles, right? It is having a thin film of soap, right? Yeah, soap water and inside it is air, outside also air. So this is an example of bubble. Clear? Right? So I hope you understood this one, and we have talked about the extra pressure, how much is the work energy, etc. we have written, right? I hope you this much is clear. Friends, okay, if someone asks you what is the pressure inside a drop and a cavity, see, so again I'm taking it in a different form. Even if you don't take, or in the case of drop, I hope you remember I have derived what is the pressure extra in the case of drop, not in the case of bubble. In the case of drop, it is extra pressure P is equal to 2S by R. I hope you remember, right? Capital R, I believe we have taken it as capital R, right? Clear? Similarly, we talked about bubble also, right? In the case of bubble, it is 4S by R, right? Clear? So I am not going to take it again, guys. Now, let us move on with capillary rise. This is the last topic of the chapter, capillary rise. Capillary rise. Now, capilla, that is from where this capillary came. Capilla word is actually a Latin word and it means hair. So, a cavity or not a cavity, a tube-like section which is so narrow as that of hair, that is usually called a capillary tube. Clear? But most of the time we take all the tubelets as capillaries itself. The actual meaning is a tube which is having the size very small as that of hair. Clear? Now before going to the capillary rise etc. derivation, there is a small part which is not mentioned in your textbook, but you have to learn if you want to understand the capillary section clearly. See, suppose I consider a capillary tube here, right? A molecule of liquid, so, and this is having liquid, okay? A molecule of liquid on the surface near the wall, right, of the capillary is subject to two different types of forces. Two type of forces can act on this liquid molecule on the surface. One is the force due to the surrounding molecules of the liquid, right? It will be surrounded by its own natured molecules. So this is a water molecules, means it will be surrounded by water molecules itself, right? So force due to the surrounding molecules of the liquid itself, that force is called cohesive force. It's called cohesive force due to its own natured particles, right? Now there will be force between this molecule and the wall of the capillary tube, right? That force is called adhesive force, right? I hope you understood there are two types of force between the molecule, right? Water molecule, if it is water molecule, right? So force between the water molecule and another water molecules, not another one molecule, different molecules, right? That type of force is called cohesive force. Now force of attraction or force between this water molecule and the wall of the capillary tube, that type of force is called adhesive force, right? Clear? And now you can see that the liquid molecules only in one side of the wall, right? This side doesn't have wall or liquids, right? So an unbalanced, this cohesive force, you can write it as Fc, right? Adhesive force, let's say Fa, right? So we can see that the liquid molecules only are occupying one side of the wall, so an unbalanced force called Fc or cohesive force acts into the liquid, whereas the adhesive force acts perpendicular to the wall. If you want, I can show it in the figure form, right? This is a capillary tube. Let us talk about water. So its meniscus will be like this, right? So adhesive force will be acting like this. It is towards the molecule, right? And as the cohesive force, I will draw it like this, right? Clear? Right? The surface will take the shape such that the resultant force, resultant will be in this direction then, right? The resultant force of the two forces, right, is perpendicular to the surface at the point of contact, is perpendicular to the surface of the point of contact, right? Clear? Right? I hope this much is clear. Even if this doesn't look like a perpendicular, I'll redraw it like this, right? This is the resultant force. Clear? Right. Now if Fa, that is adhesive force, if it is greater than cohesive force, what is cohesive force? Cohesive force is the attraction between its own molecules. That's why we have drawn it into the liquid. Adhesive force is the force between the molecule and the wall. That's why I have drawn it as like this, right? Clear? Fc acts into the liquid and Fa outside, perpendicular to the surface of contact, not the perpendicular to the wall, right? And the resultant is in between them. This much is clear, right? Now R is perpendicular to the meniscus, right? This is a meniscus, right? Clear? That I hope this, even if, see, if you consider this as a being curve, so this is like perpendicular, right? Clear? Now if Fa is greater than Fc, then the meniscus will be concave like this, right? Now similarly I'm going to draw for the other guy, right? Here this becomes Fa perpendicular to the wall. Now Fc like this, right? R, if I consider this as a circle, R will be perpendicular, means it should be in between, so like this, right? So this becomes a resultant. So in the case of this convex section meniscus, Fc is greater than Fa, right? Keep that in mind. Clear? So in the case of
concave meniscus, adhesive force is greater than cohesive force. That is, in the case of water, the attraction between water molecules is greater than the attraction between the water and the wall, whereas in the case of mercury, the attraction between the wall and the liquid is greater than the attraction between the liquid molecules. Simple. It is better if you keep that in mind. Yeah, so just looking at the cohesive and adhesive forces also, you can say whether the liquid can spread or not. So this is very important, actually not mentioned in your textbook. I'm giving from my side. Clear? Now your textbook topic, capillary rise. Right. So I hope you understood what is the meaning of capillary. So now you're going to deal how much is the rise of the capillary. If you are having a tube, so how much height till how much height the water can rise, right? So, oh, uh-huh. I'm going to take white color again. Okay. See, due to the pressure difference across a curved liquid air interfaces, the water rises. Right, you know that, right? Water will be rising inside the tube. Even if against the gravity, you can see if you're having a tub, you dip a tube, the water will rise inside it, right? Actually, water is not supposed to rise as per you because the gravity always darts downward, yet the water rises, right?
We are going to describe why it is rising, etc. with a simple derivation, guys. So let us consider a capillary tube. I am going to keep it in a tub of water itself. Let's take water, right? So water rises. Let's say I'm going to consider this section. Let's say the pressure here is P naught and this is atmospheric pressure P atmosphere, or I can just write it as PA, right? Oh, both of them are looking like PO, right? PA. Let's say this is the height rise, right? I have drawn this capillary section larger so that you guys can understand. Capillary is usually very small, right? Let's say this tube is having, capillary tube is having, let's say having a radius. In your textbook the radius is given as A, right? So let us take it as A itself, right? Now I have drawn it as flat. Let us consider the liquid is water, so the meniscus like this, right? Right. So sorry for, let me make this a silent. Okay. Right. So this becomes A, right? And this, if I had drawn fully, right? So it will be a spherical shape, right? So this, let's say, is the radius R. This, let's say, is the angle theta, right? Right. So this is actually a water droplets radius R. So there is, I'm considering a water section. So if I consider 2 points inside this capillary tube, this one which is outside the meniscus, this is the concave side, this is concave side, and this is convex side. Clear? Right? So there is a difference in pressure between this concave and convex side, right? Because if I think it in a wide view, this is like a water droplet, right? Right, the above surface is like a water droplet. So in water case, water droplet, the excess pressure is given by 2s by r. So pressure difference between these two sides, I can write PO minus PA, or it is better, which is greater, atmospheric pressure is greater, right? So PA minus PO, right, is equal to 2s by r. Right, let us write it as capital R. We have taken it as, no, R is radius, no? So 2s by r, right? This much is clear. Okay, now moving on, right? So we know, let's say there is a pressure difference, right? That is the pressure just below the surface, that is on this convex side, is actually very less when compared to this pressure, right? So this is atmospheric pressure, right? Pressure on the concave surface, this concave surface is atmospheric pressure. I wrote here, that went off, right? This is atmospheric pressure, and the pressure just below, that is in the convex side, is PO, and we know that atmospheric pressure is greater when compared to the P naught. There is a pressure difference just below the surface, right? So I can say actually P naught is equal to P atmosphere pressure minus 2s by r, Why did I write capital R? I am repeatedly writing capital R. 2s by r, right? So there is a pressure less here, right, to maintain the equal pressure, right, so that the pressure becomes equal. This P naught pressure should be equal to PA. That's what it wants, right? It wants to maintain the pressure difference, has to be nullified to have an equilibrium. So till when will the capillary rise? Till then, the point when both the pressure PA and P naught equals to 0, right? At that time the rising stops, right? So the level will rise till a height h, so that this h is causing a pressure h rho g, right? That is equal to 2s by r. If you didn't understand, I can even take it in a different term. You have learned in the case of a liquid surface, if this is a pressure below and this is the atmospheric pressure, what is the difference, and this is the height, what is the difference between PO and P net? You have written as H rho g. So we can even substitute in this section also, right? I want to make you understand why it is rising, that's why. So it is P naught or PA minus P naught, you have learned it as H rho g, that is equal to 2s by r, right? Then from here I can write h is equal to 2s by r, 2s by r rho g, right? Now I can write this r in terms of capillary tube, because we are talking about capillary. So let us just enlarge this figure, right? So in this figure, what can I talk about r and a? What is cos theta? Cos theta is equal to a by r, or I can write r is equal to a by cos theta, or a cosec theta, so not cosec, sec theta, right? A sec theta, right? So r is equal to a sec theta. So here I can just substitute the equation here, so that h is equal to 2s by a sec theta. Why did I write c theta? Sec theta rho g, or 1 by sec theta is cos theta. I can write h is equal to 2s cos theta by a rho g. This is a general formula for capillary rise, and usually h into r, this h into a value is constant. H into a value is usually constant, and this is called Jurin's law. This is not there in your textbook, this is from my side, right? Clear, right? So I hope this much is clear now, right? Not that much of talk. And there is an see, now the small section which I am going to take, this by this the entire topic is finished as per your NCERT. Now small topic which I am going to take is need section, that is tilting of a capillary tube. That is when the tube is tilted. Suppose let a liquid is there and it is rising by an h in a capillary tube, and the tube is tilted, let's say by an angle, let's say alpha, to the vertical, let's say not horizontal, I took it as horizontal. Suppose this is a vertical section and this capillary tube has, initially this was the condition, had a capillary rise of h, right? I tilted it by an angle alpha with the vertical, right? So then let's say length of the liquid column inside the tube, now suppose it changed by, let's say initially the length was some value, right? Now due to tilting, obviously, see, I hope you understand, initially like this the condition, now tilting means it will be tilting like this now, right? So there will be a small rise in the length, right? Small column rise, let's say that length is L. So L is equal to h cos alpha, right? Usually h is this one, right? So this one is h, right? So L is equal to h cos alpha, right? This is an extra topic I am just giving. That is when a liquid column is having a tilted, alpha I place here, I wrote it as theta, please change it to alpha. So if it is alpha angle tilted to a vertical direction, there will be a small shift, right, inside the column. That shift is given by L is equal to h cos alpha. Clear? Right. Now similarly, if the capillary rise in a tube of insufficient height, that is the liquid rises to the top, right? That's much you know, but the liquid will not, suppose this is the water column and I've dipped a capillary tube, the liquid is not going to come outside of the this capillary tube, right? It is not going to overflow. In this case, the radius of the free surface of the liquid, right? Right, it increases from say small r to small another value, let's say r dash, and the angle of contact also changes from say by theta to theta dash, such that in this case the h by cos theta, right, the angle of contact is not going to change, right, and this h is also not going to change, right. Simple thing which I want to increase and make you understand is, if you are having a capillary tube and you're dipping it in some liquid, you will see that never the water is going to overflow. It will never flow because always this height is always made constant. Because see, ouch, here you can see in the equation section that h is equal to 2s cos theta by r rho g. You are having rho constant, yes, g is constant. You are having the same capillary tube, so r is constant, and surface tension is also not going to change. So h by cos theta is always constant for a capillary tube, right? So whenever you say that h might rise, then correspondingly the theta will also change. So h by cos theta is always constant. That's why even if you have the rise the water section, correspondingly the angle of contact is adjusted. So whenever you are having a capillary tube inside and it is dipped in water, overflow condition never comes up, because when h increases, correspondingly the cos theta section decreases. Cos theta section or angle of contact will change. Clear? So that condition never arises, that you are having an overflow condition never comes up. Some of the few points I want to finish off, while I can say from the next video we can do the numerical section. One is effect of temperature on surface tension. That is how the surface tension changes with temperature. It is, see, when the surface tension of the liquid generally decreases with the increase in temperature. When the temperature increases, the surface tension decreases, and vice versa. And the surface tension is 0 at boiling point. At 100 degrees Celsius, surface tension is 0. And also the surface tension vanishes at critical temperature. At critical temperature, right, the surface tension doesn't even exist. It will not be there, right? So I cannot say it is 0. 0, it is usually at 100 degrees Celsius. That means it can change from when the temperature changes. It can still influence surface tension. But once the critical temperature is attained, the surface tension you cannot even see. It cannot come back even. Clear? Now similarly, so I hope you understood. So similarly, since we have talked about surface tensions, dependency on temperature, we'll talk about angle of contact also. This angle of contact will increase with the temperature increase, right? And similarly, angle of contact decreases when you are adding impurities. If they there is a lot of impurities, the angle of contact decreases, right? If you say waterproofing agents, right, it increases the waterproofing agents, right, that is coatings, right, wax coatings, etc. It increases the angle of contact, right, as well as increases the surface tension, right. And suppose what happens, you are adding detergent, right, it is what is happening is it decreases the surface angle or angle of contact, hence the surface tension will be also decreased, right. That's why a detergent is used for removing the dirt section. Clear? So this one is very important. So we have talked about working of detergent. There I missed out this point, why we are using detergent. It reduces the angle of contact, hence decreasing the surface tension, right. So it is very easy for the liquids to flow out, right. Clear? And hence that removes the dirt from the grease sections. Clear? Right. Now I would suppose we'll do a small problem. See, a water droplet is there, right? Let us say it is having a radius 10 to the power minus 2 meter. It is broken into 1000 equal droplets, equal size droplets. If the surface tension of water is 0.075 newton meter or newton per meter, you are asked what is the gain in surface energy, right? So I will do it by a roundabout way, right? So we know that the original drop is having a volume of 4 by 3 pi r cube, and you know the value of capital R is given as 10 to the power minus 2 meter, right? And if R is the small droplet, right, its radius, its volume will be 1000, 10,000 amount of molecules, right? 4 by 3 pi mole r cube. So you can find small r. I have actually given you the formula, n raised to what, minus 1 by 3 into capital R, right? So I can write this as n is 1000, right? So it becomes r by n raised to 1 by 3, or what is the r's case? It is 1000, not r, 1000, just 10 to the power minus 2 na? So I will just write it as r. What is n? 10,000. 10,000 raised to 1 by 3 is 10. So I will get the radius of the small drop is equal to 1 by 10th of the radius of the larger drop. Now what is the surface area of the original drop? Let's say it is A1. It will be 4 pi capital R square, right? What will be the surface area of 1000 droplets, right? So it will be A2. That will be 4 pi, right? And in terms of it is small r square, right? So here I can write in terms of capital R, it will be 4 pi r by 10 whole square, right? Clear? And there are n number of droplets, right? So I have to write 1000 here, right? So it will be what? This will be 100, and there will be 40 pi r square. That will be the area of smaller droplets, area of the larger droplets. What is the increase in area now? You can just find the difference of it. 40 minus 4 is 36 pi r square. That is the change in area or increase in area, right? Now gain in surface energy is equal to what? Change in surface energy is equal to surface tension into area or area change, right? So I can say what is the area change here? 36 pi r squared into s. Now you just have to substitute the values. 36 pi is 3.14 and radius square is 10 to the power minus 2 square, and surface tension is given 0.75. You will get the value as 8.5 into 10 to the power minus 4 joules. Clear?